Hi everyone. In this video, I'm going to try to teach you a couple new techniques for integration or anti-differentiation. The first one is using long division to integrate a rational function. So let's begin with example 1, which will be the integral of 4x plus 4 divided by 2x minus 1 dx. Okay, now some of these, like this one, can actually be done by U substitution, but I want to teach you this other method. You're noticing it's a rational function. A rational function is a polynomial over a polynomial. In this case, it's just a linear over a linear, but it's a rational function. So if the degree of the top is greater than or equal to the degree of the bottom, right? Top degree greater than or equal to bottom degree, I think you can use this technique. So we're going to do long division. You can also use synthetic division. If you learned that, I hope you did in Algebra 2 or Pre-Calc. But let's do it with long division. We're going to divide 4x by 2x to get 2. Then we multiply 2x times 2 and negative 1 times 2. And we're going to subtract. And so now I have an answer, which is going to be 2 plus 6 divided by 2x minus 1, right? This is my long division. So now this integral is equal to 2 plus 6 divided by 2x minus 1 dx. Okay. And now I can integrate it. The first piece just becomes 2x. The second piece, I'm going to use a U substitution for, okay? And I just make a simple U substitution. U is equal to 2x minus 1. du dx is equal to 2. So dx is du divided by 2. I will come and put that back into my integral here. So I have 6 over u, and then dx is du over 2. So I'm going to end up with 2x plus 3, and I can pull the 3 out, du over u, which means this is 2x plus 3 ln absolute value of u. And now my last step will be to put it all back in terms of x. So 2x plus 3 ln of the absolute value of 6 over 2x minus 1 plus c. This will be my answer. Let's do another example of integration by long division. Let's do number 2, which is going to be the integral of 3x squared plus 5x plus 3 over 3x minus 1 dx. It's an indefinite integral. So again, I'm noticing that the numerator degree is 2, the denominator degree is 1, so this technique should help. So let me go off to the side here to divide 3x squared plus 5x plus 3 divided by 3x minus 1. Just reminding you how to do this, we divide the front by the front. 3x squared divided by 3x is just x. Then multiply 3x squared and negative x, then subtract, and then bring down. So I bring down the 3. Then divide again this leading term by this leading term to get plus 2. Multiply 6x minus 2, subtract to have a 5 down here, and nothing left to bring down, right? So my answer to the division problem, which is what I have to write in the integral now, is x plus 2 plus, this is a plus 5, so it's plus 5 over 3x minus 1 dx. Okay, so the integrand, when you do this, becomes a few things that you can just integrate easily, like x squared over 2 plus 2x. And then this piece, this last piece, right, this is going to become a simple u substitution. And the u is going to be the denominator. So the u will be 3x minus 1. The du is going to be 3 dx. And so dx is du divided by 3. And you will just come back and do this little integral here. you can pull the 5 out front, and then we have the integral of du over 3u. The 3 will now also come out front, and so you're going to be left with 5/3 ln u, and we're gonna substitute that 3x minus 1 back in for the u. So there is my final answer to that one. Okay, let's do another one. Let's do the integral of x cubed plus x over x minus 1 dx. Okay, and again, the top has a degree 3, the bottom has a degree 1, so we can divide. Okay, so let's go off to the side and divide x cubed plus x by x minus 1. And I'm going to use this to just review a few things about division. The first thing is that this is the dividend and this is the divisor. And we want to make sure that there are no missing powers in the divisor. Like here, for example, there's no x squared. So then I have to add a 0x squared when I write this out. And then we put the divisor here, right? So that's the first thing to remember, add in any missing powers. The second thing to remember is that we're going to keep on dividing until the degree of the remainder is less than the degree of the divisor. Or until there's nothing left to bring down. Okay, so let's see how this works. So here I'm going to start again by dividing just the front term here by the front term here. So I get x squared, then multiply x times x squared and negative 1 times x squared, then subtract, and then bring down, okay? Then divide, again, the front term by the front term, so we get x on top, multiply, which we get like that, and then subtract, so we get 2x, right? And there's nothing left to bring down. However, the degree of the remainder, which is down here, right, is not less than the degree of the divisor. So I have to keep going. So I add a plus 2 now up here, again dividing the 2x by the x, multiply, subtract, and I'm left with a 2 on the bottom. So now I have, of course, nothing left to bring down, and the degree of the remainder, 2, is less than the degree of the divisor. So now I can stop, and I can go back into my integral and rewrite it as x squared plus x plus 2 plus 2 from down here, remainder over divisor, and all of that dx. Okay, and now you see how it's broken down into a much easier integral. In this case, I don't even need to do a u substitution because it's a special case of a u substitution where the inside function would have a slope of 1, and so I can just write my answer, which would be right here. Okay. Okay, let's practice one last one, which is this one, integral 4x cubed over 2x plus 3. Okay, so let's go over and do our division. 4x cubed divided by 2x plus 3. I'm going to add in a bunch of 0 powers here. And then I can say 2x squared on top, then multiply this and this. So I get 4x cubed plus 6x squared. Okay, now we're going to subtract and then bring down. And then again, divide to get negative 3x. Negative 6x squared minus 9x, subtract to get plus 9x. This right here, I wrote 0x, but it's really just 0. Okay, and I can still divide because my divisor and my remainder are equal degree, right? And I want to keep going till the remainder is lesser degree than the divisor. So I'll say plus 9 halves. 9 divided by 2, or 9x divided by 2x. And then I get here 9x plus 27 halves. And so now my remainder is negative 27 halves. Okay, so coming back into the integral, I'm going to write that quotient there. So that will be 2x squared minus 3x plus 9 halves, and then minus 27 divided by 2 times the divisor, right? That's 27 over 2 divided by 2x plus 3, okay? And all of this is my new integrand, and this is going to now be equal to, now I do the antiderivative of each piece. So I'll get 2/3 x cubed minus 3 halves x squared plus 9 halves x. And now this becomes a u substitution. So I'll go negative 27 over 2, the integral of dx over 2x plus 3. My u will be equal to 2x plus 3. Du dx is 2, so dx is du divided by 2. And I can finish this off like this. So I have negative 27 over 2, and then the integral of d, actually be 2d, yeah, du divided by 2, and then here's my u. So that would be it. And so, almost done, this will be 2x cubed over 3 minus 3 halves x squared plus 9x over 2 minus 27 over 4 ln u. And when I put back the 2x plus 3 for the u, I will end up with this as my final answer. Okay, so these integrals now are going to be related to the arctangent, right? Because we know that the antiderivative of 1 over x squared plus 1 dx is arctan x plus c. So there are some integrals that are related to this, which we can do by u substitution or by completing the square or by both of those. So let's see an example that would be kind of the simpler case would be something like this, where you have 1 over x squared plus 4 dx, right? So we see that we have a 4 here and not a 1. So to deal with that, we would just divide by that 4. And we would say this integral is the same as divide the top and bottom by 4. And so you would get 1/4 on top, and on the bottom we would get x squared over 4 plus 1 dx. Now this can be written as 1/4 comes out front, and then 1 over x over 2, the quantity squared plus 1 dx. And now you can do this very easily with a u substitution of x over 2. So du dx is 1/2. So dx is 2 du, and I can go back in here and say this is 1/4 2 du over u squared plus 1. And so the 2 comes out, and I'll have 1/2 out front, and then I have an integral that looks exactly like my arctan integral up here, right? So this looks exactly like this, and so the integral of this is going to be equal to arctan 1/2 from out front, arctan u plus c, and arctan u is arctan or tangent inverse, right? This could be written as tangent inverse x over 2, okay? Just recognize this right here, right? It's saying the same as this. These two things mean the same, okay? Okay, so that is the simpler case of an arctan integral. Number on the top, something close to what we want on the bottom, but a number here instead of 1, right? So then you divide out the number and then write this term as a perfect square and use that as your u. Okay, what happens when you have 3 terms on the bottom? You might have a problem or a situation that looks like the integral of 1 over a quadratic on the bottom. But this quadratic has to be worked on to get it into a format that allows us to use our arctan formula, right? So it's going to again involve u substitution, but before the u substitution, we want to complete the square. How do we complete the square on a quadratic? Well, we take the x squared and the x terms, right? So it's x squared plus 4x. This is ax squared plus bx, right? So we want to identify our b, divide it by 2, and square that. B divided by 2 is 2. 2 squared is 4. So completing the square on this is going to mean saying this is equal to x squared plus 4x plus 4 minus 4. We don't want to change the equation. We're just rewriting it as a perfect square trinomial. And then we're going to have a number on the end of that, right? It's like taking a standard form parabola and writing it into vertex form. Okay, so now we've got that, and we're going to substitute that into the integral, right? So I'll write it over here. We'll take this integral and put what we found here in. So this is x plus 2, the quantity squared, minus 4 plus 8 dx. So now I have integral 1 over x plus 2, the quantity squared, plus 4. Okay, so now I'm starting to get close to the form I want, except I don't want a 4 here again. I want a 1. So I will divide everything, top and bottom, by 4, and I'll get a 1/4 out front, and then on the top, I'll just get my 1 and the dx, and then here, the 4 over 4 is going to become 1, which is what I want, and here I'm going to put that inside the square, like this, right? So now I can call this thing inside my u, just like before, similar, right? And I'll say u is equal to x plus 2 over 2, or x over 2 plus 1, du dx is equal to 1/2. So I can now do my u substitution. dx is 2 du, so I'll have 2 du and then 1 over u squared plus 1. The 2 will come out front and cancel with this 4, so I'll have 1/2. 2/4 becomes 1/2. 1 over u squared plus 1 du. And again, this is the arctan, or tangent inverse, of u plus c. Now, u was the yellow thing up there, so it's 1/2 tangent inverse of x plus 2 over 2 plus c. Okay, so this is how you deal with integrals where you are seeing a quadratic on the bottom and a number on the top. You want to try to transform it into an arctan integral. I'm going to do one more example here, and this is going to be an example of completing the square when the leading coefficient is not 1, right? So for example, here is an integral, and we're seeing that the pattern is we just have, it's really just 1 over this stuff. It's a 1 over a quadratic. So we're thinking completing the square is an option, but the leading coefficient here is 2. So in a case like this, we want to pull that 2 out first and complete the square on the quadratic here, right? So completing the square on that would mean b is -6, so b over 2 is -3, and that squared is +9. So I would have to add 9 inside the parentheses, right? So I'm really going like this, adding this 9, which means I've really added 18 to the equation. And remember, the goal is you're not changing the equation, you're just rewriting it. So if I've added 18, I need to subtract 18 from the equation to keep it the same. So now I have a perfect square trinomial here, and outside I have 26 minus 18, which is 8. Okay, now at this point, in this particular one, you can see there's a 2 here and an 8 here, right? So I could just pull out a factor of 2 and write this as 2 and then x minus 3 squared plus 4, which means I can bring a 1/2 out of the integral, so I might do that. and then I'm looking at this integral. Now this is looking almost good for an arctan, except we don't want a 4 here. We want a 1, right? So we're going to divide everything top and bottom by 4, which means I now have this 1/4 will come out. I'll have 1/8. And then down here, I have my 1, which I want. And this, remember, has to be written as something all squared. So there is, I'm going to put the 2 in and square it, right? This 4 inside a square. Okay, and I think now we're ready for the u. U is equal to x minus 3 over 2. Du dx is equal to 1/2. So dx is equal to 2 du. And so then I can come back in here and say 2 du over u squared plus 1. The 2 will come out, so I'll have a 1/4 outside, and I have now an arctan integral. So this is 1/4 arctan of u plus c, and u was equal to x minus 3 over 2. So that's the final answer. So the moral of that story is that if you have a 2 as the leading coefficient on your quadratic, be careful when you complete the square. You have to factor the 2 out, and you have to think about when you add in the number to complete the square, it's being multiplied by that 2, and so then you have to subtract off the right number. Okay, this set of questions is going to be about the arcsine integrals, right? And those are the antiderivative we know of 1 over rad 1 minus x squared. That's the one which is equal to arcsine of x, or sine inverse of x, right, plus c. So first type of problem is when you see 1 over square root of 9 minus x squared, right? So notice it's similar to this thing up here, but I have a 9 instead of a 1. So these are fairly easy in that what we need to do is divide by that 9. Now we're inside a square root, so we're dividing by 9 inside a square root here. So that means outside the square root on top, I would divide by 3. So then I have 1/3 out front, and then I have 1 dx, and on the bottom, square root of 1 minus x over 3, the quantity squared. So now you just proceed to say u is equal to x over 3, du dx is equal to 1/3, dx is equal to 3 du, and now you can come back here and rewrite this integral as 1 over the square root of 1 minus u squared. 3 du goes here, and the 1/3 out front, those 3's are actually going to cancel because this 3 can come out, and so I'll be ending up with 1 over the square root of 1 minus u squared du. And so my answer here will be sine inverse of u, because now it's in exactly the format I want, or arcsine of u. Now u is equal to x over 3, so this is what we're saying is our final answer, sine inverse or arcsine of x over 3. Okay, things can be more complicated with the arcsine if you have, maybe you don't have a 1 on top, you have a number, that's okay. But the complexity might come from what's inside the square root, because what's inside the square root may not look like, the first one we did, it was just like square root of 9 minus x squared, which you just had to divide by this 9, right? But here it's more complicated. You have an x term as well. So we're going to use completing the square, right? So for this, we need to remember that we want to first just go take this 12 minus x squared minus 4x. Okay, and we're going to complete the square. So to complete the square here, we'll factor this minus out, pull out a GCF. So then we have 12 minus x squared plus 4x plus 4. This 4 is really a negative 4, so I have to add 4 outside the parentheses. So 16 minus x plus 2, the quantity squared, that's my completed square, right? So now I can take this integral and rewrite it as the integral of 8 dx over the square root of 16 minus x plus 2, the quantity squared. Now, like before, I don't want the 16 here, I want 1. So I'm going to divide by the 16. So I get 1 minus x plus 2 quantity squared over 16. I'm dividing by a 16 which is inside a square root. So I'm really dividing by 4. So on top, where I have no square root, I have to divide by 4. We're dividing the top and the bottom by 16 inside the square root on the bottom, so 4 on the top. So then I can say this is 2, and then I have dx, and now this looks like what I want to see before my u substitution. I'm going to put the 16 into the squared and write it as 4 squared. So u now has to be equal to x plus 2 over 4, which is 1/4 x plus 1/2. So du dx is equal to 1/4, and dx is equal to 4 du. So I'll have a 4 du here, and then square root of 1 minus u squared here. So I'll end up with 8 integral of du over square root of 1 minus u squared. That is 8 arc sine or sine inverse of u plus c. So I'll write it as 8 sine inverse of x plus 2 over 4 plus c. That's our final answer. Okay, we'll do one last example of an arc sine integral. So I want to integrate 1 over the square root of negative x squared minus 4x plus 21. Okay, so I'm seeing the square root, I'm seeing a number on top, and the quadratic inside the square root. So I should be thinking of an arc sine completing the square situation. So we are going to do that. So we are going to first pull out the, put the number first. So say 21 minus x squared minus 4x. And then you want to pull that negative sign out. So we're going to think of it this way. So it's 1 over the square root of 21 minus x squared plus 4x. Okay, so once you get it there, you are going to complete the square. So go off and think about completing the square. So it's x squared plus 4x, b is equal to 2, b over 2 is equal to b is equal to 4, b over 2 is 2, and so the square of that is 4. So we're adding 4 inside this parentheses, which means I have to think I have this negative sign here. So if I'm adding 4 like this inside the parentheses, then that means I've really subtracted 4 from my equation. So I need to add 4 outside the parentheses. So now that gives me 1 over 21 plus 4, 25, minus the perfect square here, dx. Okay, so remember we want a 1 here and not a 25. So we're going to divide the inside of the square root by 25. So I will have 1 over the square root of 25 divided by 25 is 1 minus x plus 2, the quantity squared, divided by 25. Now I need to divide the top by the same thing. So since I was inside the square root on the top, I have to divide by the square root of 25, which is 5. On the bottom I was inside the square root, so on the top I need to divide by 5. So I now have 1/5, and that can come out, integral of 1 over square root of 1 minus x plus 2 over 5, bring that 25 into the square root, write it as 5 squared dx. And so this is equal to 1/5 integral, and I'm now going to do my u substitution. U is equal to x plus 2 divided by 5. Du dx is going to be x plus 2 divided by 5 is the same as this. So that's 1/5, and dx is 5 du. So I can say 5 du over here and square root of 1 minus u squared over here. The 5 can come out and it's going to cancel with this 5. So I'll just have, those will go away, and I'll have the integral of 1 over square root of 1 minus u squared, which is, of course, what we want to see. This is sine inverse or arc sine of u plus c, and we can express this again back in terms of x. So it's sine inverse of x plus 2 over 5 plus c.